Hello, this is Duhyeong Kim for Intel Labs, and today I'm gonna talk about our recent work on the high-precision RNS-CKKS on small word size architecture. This is a joint work between Intel Labs and Seoul National University. So let me start with a brief overview of what this work is. So in this work, we basically enable high precision RNS-CKKS on fixed but smaller word size architecture. So in the original CKKS related papers, we usually use a single scaling method, but which sometimes cannot be used for the small word size architecture. So we developed a new technology called composite scaling, and we enable the functionally correct CKKS composite scaling in two open source library. One is OpenFHE and the other one is Latigo. So basically, we try to demonstrate with the secure parameters the equivalence between the single scaling and the composite scaling. So I haven't explained the definition of single scaling or composite scaling, but you can just understand as the equivalence between the original framework and our new framework that is that can be properly used for the small word size architecture. So we experimentally prove this equivalence on the workloads we have internally, including the 7-layer CNN inference with two different packing methods, and the other one is logistic regression training. Okay, so let me just start with the brief definition of FHE. I mean, it is a bit weird. It can be a bit weird to explain the definition of FHE at the fhe.org, right? But let me very fastly go through the slides. So as you know, the homomorphic encryption is crypto system which allows the computation on encrypted data without any decryption process. So theoretically, when we encrypt the data with homomorphic encryption or FHE, then actually we can do any computation and any like data analysis in real world, even without knowing the data itself, which ensures the data privacy. So after the Gen 3's first FHE instantiation based on the ideal lattice, there have been proposed a number of FHE schemes, and there is this several branches of different type of the FHE schemes, and CKKS is one of very recently proposed FHE scheme, which support real number arithmetic. So how can we think of the approximate computation? So I mean the fact that CKKS support real number arithmetic, it just means that with CKKS we can homomorphically do the approximate computation over real numbers, right? And then the natural question would be, how should we think of the approximate computation in CKKS? Then, briefly speaking, you can very easily regard it as the imitation, very simple imitation of fixed point arithmetic in clear text version. So let's look into the example together. So here's the very simple example, the multiplication of several real numbers, right? So the given figure can be applied to both clear text fixed point arithmetic and also the CKKS. I mean approximate computation in CKKS. So for now, let's just think of the clear text version without considering CKKS. Then when we want to multiply those given real numbers with fixed point arithmetic, then what we should do as a first step is we need to scale up the given real numbers to convert them as a fixed number, which has the form of integers, right? So we need scale up procedure with some proper scaling factor. And then we can proceed the multiplication. But as you can see, when we multiply like two fixed numbers, I mean fixed integers, then you can just easily see that the bit length, the size of the numbers exponentially grows up, right? So, like for example, when we multiply the first two numbers, like 158K times 248K, then it becomes much larger, right? So if we just multiply them without any other additional procedure, then the number should be the bit lengths of the numbers will be increased exponentially. So to prevent that, in fixed point arithmetic, we take the scale down procedure to keep the scaling factor as some fixed value, right? So as you can see, after a single multiplication, we scale down by the same amount of the scaling factor so that the resulting value will have the same scaling factor. So the rest of the process are very simple: multiplication and then scale down, and multiplication and then scale down, and so on. So as a result, when we do repeat this procedure till the end, then we will have some resulting fixed number. So after the last scale down procedure, we will finally obtain the approximate result of the given computation, right? So what we need to note is that regardless of whether it is clear text version of the clear text fixed point arithmetic or CKKS approximate computation, the framework itself is exactly the same. The only difference is that when we want to interpret this figure as a CKKS approximate computation, then we just need to add the procedure for the encoding and encryption process at the beginning of this whole process. So now let's come back from the real example. So basically, here what we can question ourselves is that what is the role of this scaling factor in CKKS as well as fixed point arithmetic? As we've seen in the previous example, actually the CKKS encoding and encryption process, it will result in the transformation from the given real number m into delta times m plus e, where here delta refers to the scaling factor and the e is some error induced by the encoding and encryption process. Here this error e, the size of the error e is fully determined by the other FHE parameters such as dimension, secret key distribution, error distribution, and so on, which are independent to scaling factor. So from this observation, what we can easily see is that scaling factor determines the initial precision bits under the decimal point. So if we set a larger scaling factor, then we start with higher precision. And if we set a smaller scaling factor, then we start with lower precision. So how large we need to set this scaling factor, it depends on what is our target workload or our target circuit to evaluate. One other thing we also need to notice is that as I mentioned in one of these previous slides, scaling factor actually exponentially grows up for each level of the multiplication if we do not put any other additional procedure. So in the previous figure, that was the reason why we have scaled down procedure in fixed point arithmetic. So in CKKS, we also need some corresponding homomorphic evaluation algorithm, right? And that is called rescale. So in other words, rescale is homomorphic evaluation of scale down procedure. The algorithmically, the rescale procedure is very simple. So when the ciphertext is given, then so this expression modulo delta power L. I brought this notion from the context of original CKKS. So in the original CKKS, how we define this rescale is that when the ciphertext modulo delta power L is given, then we compute the rounding of ciphertext over delta modulo delta power L minus 1, right? So with this rescale procedure, then what we can do is after a single multiplication, the scaling factor goes up to delta square, but by the rescale procedure with delta, then we can bring the scaling factor back to the delta. So we can always keep the corresponding scaling factor of each ciphertext to the delta. Right. So this was very brief summary of the role of the scaling factor in the original CKKS. And now let's look into how different this rescale algorithm is in the RNS instantiation. So the RNS variant of the original CKKS, which we usually call RNS-CKKS, actually it gives much more efficient implementation because we do not need to use big number arithmetic contrary to the original CKKS. So in RNS-CKKS, the main difference on the setting is that we use the ciphertext modulus, let's say QL for the level L ciphertext. We use the ciphertext modulus as the multiplication of distinct primes instead of modulo delta power L. So roughly speaking, we represent all the objects in the scheme. I mean, all the ciphertext related objects in the scheme within the RNS representation, where the RNS representation means that rather than we represent some information of the big number as itself, we split the information into multiple small numbers by taking modulo different primes, so that we can restore the original big number information through the inverse CRT operation. So now what we need to see is that how the rescale procedure becomes differently in RNS setting of CKKS. So why the reason why I'm talking about this is that, as I mentioned, in the original CKKS, we just consider modulo delta power L. So multiplying by 1 over delta and then taking rounding, it was a kind of natural operation, not algebraically natural, but natural in the sense that we can naturally reduce the modulus from delta power L to delta power L minus 1, right? But in RNS representation, unfortunately, there's no efficient way to compute rounding 1 over delta power times x within the RNS, like RNS representation with modulo some QL, right? But instead, what we can do is we can actually efficiently compute the rounding 1 over QL times x instead of rounding 1 over delta times x, right? So one thing you can easily one easy way to understand this operation is you can actually regard the rounding of 1 over QL times X as the quotient value of the integer division of X by QL, right? Then and also you can regard X modulo QL as the remainder for the integer division of X by QL. So because we have a very clear relation between quotient and remainder, we can have the identity this equality that the rounding 1 over QL times X equals to QL inverse times X minus X modulo QL, which is remainder, right? Then the only remaining thing we need to see is that what is the RNS, because we already have RNS representation of X. So the only remaining thing we need to see is the RNS representation of X modulo QL. But this is what we actually already have, right? Because RNS representation of X modulo QL is just, you can just copy the value X modulo QL for each of the position, assuming that each of QI are in this similar size. So in short, when we get into RNS representation, the original Rescaling algorithm cannot be efficiently computed, but we can find alternative way for the division and rounding operation. So now we have a tool to take rounding 1 over QL times X computation, right? So let's think about this case one. So when the scaling factor, the log scaling factor is smaller than the given word size, so the given word size from the architecture, then what we can do is we can actually set QL to be quite close to delta. Then this means that 1 over QL is also very close to 1 over delta, right? Then this means we can actually support a very similar functionality to the original Rescaling in the original CKKS, even in RNS-CKKS, right? But on the other case, right, in the remaining case, which means we want to set very quite large scaling factor, which is even larger than the given word size, right? That can happen always, right? In that case, we cannot have the same setup with the case one, because when when the word size is smaller than scaling factor, then each of prime QL cannot be even log delta bit, right? So in this case, we will have two choices. So the first very simple choice would be just use multi-precision library. So multi-precision arithmetic to perform some 64, like for example, a 64-bit arithmetic with given the 32-bit system, right? But that is always not very preferable because there's a lot of computational waste, right? The computational overhead by just using the multi-precision arithmetic. But if we use a new technique, actually new but very simple technique, which we call composite scaling, we do not need to consider the multi-precision arithmetic. So the idea is very simple. Instead of taking multiplying by 1 over QL, 1 over single prime, we can consider to multiply by 1 over QL times QL minus 1, right? And then what we can do is we are not able to set each QL to be close to delta, right? But what we can do is QL times QL minus 1 becomes close to delta, right? Even if log delta is larger than word size. I mean, of course, in this case, we need assumption that the word size is still larger than the 1/2, a log delta over 2, right? But in that case, we can achieve we can achieve that QL times QL minus 1, the product of multiple primes, to be log delta, right? So in so we can also even consider the more extreme cases, right? What about word size is, log delta is even larger than 2 times word size, right? Then in that case, we can use triple composite scaling, right? So here, the number of primes we use for each of the rescale procedure, we call it as composite degree. So in this case, the composite degree is 3. And with this composite degree 3 case, we can cover the case that when the word size is larger, word size is smaller than log delta, but larger than 1/3 log delta. So in general, we can consider arbitrary composite degree so that we can cover arbitrary case in sub cases in case 2. So to help your understanding, I brought this very simple example, right? So for example, in our usual architecture, like 64-bit architecture, then if you want to set a scaling factor to be a log scaling factor to be 30 in 64-bit architecture, then of course we do not need to use any scaling composite scaling technique. We can do everything with single scaling. And in this case, when log delta equals to 30, then it is in this case, it is also the same for the 32-bit architecture. We can still use single scaling. But when we increase when we target a bit larger scaling factor, for example, log scaling factor to be 50, then in the 64-bit architecture, we can still use single scaling. But in word size, in 32-bit architecture, then we cannot use single scaling without multi-precision arithmetic. So the alternative way we need to choose is composite scaling. With double prime composite scaling, we can still support log scaling factor equals to 50. And the same logic can be applied to even larger scaling factor. So if we target log scaling factor to be 70, then even with 64-bit architecture, we need to use composite scaling unless we want to use multi-precision arithmetic. So now let's see how this rescale algorithm affects the precision in CKKS computation. So algorithmically, as you can notice, it is quite simple, right? Previously, we divided by 1 prime, but now we just need to divide by multiple primes. So in rescale, that is the only, algorithmically, that is the only difference. But RNS-CKKS itself is quite tricky, so we need to see how this kind of change can make the difference in the precision analysis. So actually, in original CKKS, there's no precision issue other than the rescale error itself, because scaling factor is always preserved as exactly the delta value itself, right? We always have delta, and after multiplication, it becomes delta square, and we divide by delta exactly, right? Then the resulting scaling factor should be delta. So there will be no issue regarding, there will be no precision issue because that comes from the rescale procedure. But in RNS-CKKS, the situation is totally different. So there exists precision issue. And that is because scaling factor, the corresponding scaling factor of the intermediate ciphertext during the whole homomorphic evaluation, it is not preserved as our initial target as scaling factor delta. And that is because we divide by QL instead of delta. And it is obvious that if QL is not equal, if QL is not delta, then delta square over QL, that should not be delta, right? They are not equal. So because of this reason, in general, when we perform like various homomorphic operations, including rescale, right, in RNS-CKKS, and when we list up several ciphertexts, then each of the ciphertexts should have different scaling factor. And what is the impact of this situation? Actually, there exists the critical impact to the homomorphic addition part. So basically, we never expect like homomorphic addition gives some critical precision loss, right? Like for example, when we imagine like previous FHA schemes like BGB and BFV, addition never gives some critical issue, right? When we just add two ciphertexts, then the error is also E1 plus E2. That's all. But in CKKS, I mean, in RNS version of CKKS, that is not the same. So let's say we have two ciphertexts which have different scaling factor. One has delta and one has delta prime. Then when we add these two ciphertexts, one is the encryption of delta times m, and the other one is the encryption of delta prime times delta. Then you can easily see that when we regard the corresponding scaling factor of the resulting ciphertext should be delta, then it becomes the encryption of m plus delta prime over delta times m prime, not the m plus m prime. Which is what we wanted, right? Because what we just wanted was adding two message. We wanted to obtain encryption of m plus m prime. So what this means is that the ratio delta prime over delta directly harms the precision of the internal message in the ciphertext, right? So this is a very critical issue. When we do not carefully choose the parameters or related to this risk. So we need a solution, and the first very trivial solution would be to choose the RNS primes properly so that we can keep the scaling factors to be very, very close to the delta. So in single scaling, so this the single scaling means you can just imagine the original CKKS without composite scaling thing, right? So in the original RNS-CKKS, what we usually have done was we just set each of prime to be very close to the target scaling factor. So if the target scaling factor is 2 to the 40, for example, then we choose each of the prime to be very close to 2 to the 40, right? Then if they are close enough, then the delta square over QL, which is the scaling factor after the multiplication plus rescale, right? This value will be, so this value cannot be equal to delta inherently, but still we can make it very close to delta, right? And that is the purpose, right? So if delta square over QL is very close to delta, then this means that the delta prime, which I introduced in the previous slide, right? The delta prime is anyway, delta prime becomes very close to delta, so that the ratio delta prime over delta is not exactly 1, but close enough to 1. So that is the purpose, the goal of this solution 1. So in a single scaling case, we can do that way. But then how about composite scaling? It is also very similar. The goal is to make delta square. So I made the example for the composite degree 2 case, right? So in this case, the goal is we want to make delta square over QL times QL minus 1 to be very close to delta, so that any other delta prime coming out during the homomorphic computation. That should be close to delta, right? Then to make this approximation, then the requirement is we need to find some proper primes that QL times QL minus 1 are close to each other and actually close to delta. So under this setting, when we compare the precision between the single scaling case and composite scaling case, then actually there is no difference in multiplication, relinearization, and rescale procedure. I mean, I'll explain what this no difference means rigorously in one of the next slides. But there is almost no difference. But the closeness of QL and the target scaling factor delta in a single scaling case, and QL times QL minus 1 and delta in composite scaling. So the closeness of these two values directly affects the homomorphic addition precision. But so in that sense, they have same bottleneck, but in practice, what you can easily check is that the requirement to set each single prime to be close to each other to target value, target a scaling factor delta, would be much easier. So this restriction is much lighter than the requirement for the composite scaling, because in composite scaling we need to set products of the primes to be close to each other, right? So the in practice, when we do not target a very large scaling factor, or just targeting like double prime scaling. So what I mean is, if the composite degree gets larger and if the composite degree gets larger, then it becomes much harder to meet the requirements for the composite scaling. So in short, the solution one is not really suitable for the composite scale. But fortunately, we have another solution, which we named as exact scaling. So I want to make sure that the exact scaling we refer here is not firstly proposed in our paper, but it was previously proposed in the one of the papers in presented in CTRSA 2021. But sorry for missing the citation. So basically, what this exact scaling means is that, contrary to the solution one, in this solution two exact scaling method, we set some exact scaling factor delta I per each level. So we will set the list of the scaling factor per level. So there will be delta 0, delta 1, delta 2, delta 3. So, and this delta i's are not required to be very close to delta. And also they are not required to be equal to each other. So this is a kind of the process to allow to set some different scaling factors for each of the ciphertext. But the thing is, by adjusting the ciphertext ciphertext scaling factors to give the specific delta I before addition, homomorphic addition and multiplication, we can force the situation that we always add to ciphertext with same scaling factor. So the solution one was to make the ratio delta prime over delta to be close to 1 as much as possible, right? But this solution 2 is more likely to be, we fundamentally avoid the situation that delta prime is not equal to delta. So we always, we only have the case that we adding two ciphertext with the same scaling factor. So with this philosophy, then you can also imagine that when we compare the precision between the single scaling and the composite scaling, as well as solution one, there will be no difference in multiplication, relinearization, and rescale. But also, there becomes no difference in homomorphic addition process when we compare single scaling and composite scaling when we use solution two. So we implemented the 32-bit RNS-CKKS with composite scaling in OpenFHE and Latigo with solution 2. So for your information, the solution 2, what we referred as exact scaling, was it is referred as flexible auto mode in OpenFHE. So the people who have used OpenFHE will know that OpenFHE CKKS will know that there is several modes, like four different modes, but the most that includes flexible auto that corresponds to this exact scaling method. So on the top of a flexible auto mode of OpenFHE CKKS, we implemented our composite scaling method, and also we enabled bootstrapping in both of the libraries. So this is the theoretical analysis on the precision. What you just need to see is that in the theorem, you can see two notations like B rescale and B composite rescale, right? So B rescale is the upper bound of the error induced by, so B rescale is the rescale error, and B composite rescale is composite scaling error. So this theorem gives the direct comparison of the error induced by single scaling and composite scaling, how different they are. And you can easily see that the ratio, which is written in this big blanket, right? This ratio is very close to 1, and approximately it is like 1 over qi plus 1, right? Then, so this is what this 1 over qi plus 1 factor implies. So this implies that composite scaling versus single scaling, it just results in additional bit precision loss at most log 1 over qi plus 1, and this is approximately like 3.3 over qi. So like for example, if we set scaling factor, so like for, let's say we targeted scaling factor to be 2 to the 64, and we wanted to use double prime scaling for a 32-bit architecture, then each of qi will be 32-bit primes, right? Then if qi is 32-bit prime, then 3.3 over qi bit is like much smaller than 1, right? So in practice, we can say this is negligible, right? So this is the reason why I noticed as no difference in the previous slides for the multiplication, relinearization, and rescale procedure. Okay, now let's move on to the experimental results. So as I explained at the beginning of the talk, we experimentally verified the equivalence of original single scaling and our new composite scaling method through several workloads we have, and one of them is 7-layer CNN inference with CIFAR-10 dataset. So we have two different implementation on this CNN workload. One is implementation in OpenFHE with longitudinal packing, which is the most simplest packing method. So with this implementation, we created several unit tests for each of the layers, including fully connected layer, ReLU layer, mempool layer, convolution layer, and additionally bootstrapping layer. And we also, so basically what we are trying to do is, given the same workload, same circuit, we link this given workload with the original OpenFHE and also link with our modified OpenFHE based on composite scaling, and then compare the precision bit for two cases, right? So for a fair comparison, of course, we use exactly the same parameters. So we set the ring dimension to be 2 to the 16, and we use scaling factor to be 2 to the 58. So what this means is that in original OpenFA, in a single scaling case, of course, we just use 58-bit primes, right? But in composite scaling case, because the scaling factor is 2 to the 58, and we will use double prime scaling, then we use 29-bit primes for this 32-bit composite scaling case. Then, as I mentioned, we can use double prime scaling because 58 is 2 times 29. And of course, we use the same depth parameter, so the overall security should be exactly the same. So composite scaling never harms the security more than the single scaling. So as a result, as you can see in the table, we got exactly the same number for the precision bits for each of the unit tests for each layer, including bootstrapping. And we also created wrote this implementation in Latigo, but in this case we used multiplex packing, which is the much more efficient way than the previous longitudinal packing when we target a small number of image inference. So in this case, we compared the end-to-end CNN inference result between the single scaling and the composite scaling. And we experimentally checked that the results match up to 5 digits. So it is like approximately 15 to 17, I guess, with precision. So this is not exactly the precision bit mentioned in the table, because this table means the precision bit exactly, but this 5-digit means when we compare the 64-bit case result and 32-bit composite scaling result. So this cannot be like referred as precision bit, but what you can see is that they work almost samely, right? That is the important point. And the other workload is we have is a logistic regression training. So basically, there exists the reference code, the open source logistic regression training code from OpenFHE organization. So we just linked this code to the public, original OpenFHE with single scaling, and our modified OpenFHE with composite scaling. And for this workload, we compared 3 cases. One is 64-bit single scaling, and another one is 32-bit composite scaling, and the other one is clear text word. And we compared how the loss function value goes differently for each iteration. And as you can see in this figure, the graphs for each of the cases almost overlaps, so it is very hard to distinguish. So it is one another strong evidence that even in large scale workloads, the composite scaling works very equivalently to the single scaling. In this case, as well as the previous CNN inference workload, we use the same parameter for the fair comparison. Okay, so in summary, in this work we enabled the high-precision RNS-CKKS on small word size architecture without using multi-precision arithmetic. So as you can notice in many of the FHE application paper, that there exist many cases that use small word size, like GPU implementation, FPGA implementation on GPU, FPGA, embedded devices like still embedded, right? So there are many of the situations that we really need to use small word size architecture. And I will not explain any details of this, but naturally, we can also achieve arbitrary precision, bit precision for bootstrapping, even in the small word size architecture when we combine with recent work related to CKKS bootstrapping called MetaBTS. So in this perspective, it looks like very just a good work with I mean just with just the advantage, but there still exists some of the limitations, like on the choice of the scaling factor. So in practice, because we want to support very efficient implementation of CKKS, most of the libraries, I think all the libraries are using double CRT. I mean, not only using RNS representation, but we also use NTT for faster polynomial multiplication, right? But to use NTT, each of the primes should satisfy some certain condition, and this certain condition results in some lower bound of the prime size, right? So, for example, what you can think of is let's say we want to use scaling factor to be 2 to the 40, but in 32-bit architecture, then because we want to avoid multi-precision arithmetic, then we will choose composite scaling. And most proper way to do this is to use two 20-bit primes for double prime scaling, right? But if we want to use the practical parameter like dimension 2 to the 16, then how many 20-bit entity-friendly primes exist, right? There will be only a few. Then this means that we cannot support large amount of depth for this kind of cases, right? So you can easily track that for when we want to use composite scaling, then there exists several small intervals that are not usable as scaling factor. So when we think of the whole interval like 0 to some number that represent the log bit size of the scaling factor, then there are several punctured spaces. So that can be a kind of the limitation in this kind of example cases, right? So we need to use large dimension like 2 to the 16, but still we don't need to use very large scaling factor, like 2 to the 40 is enough. Then composite scaling can be problematic, but this does not mean we cannot use composite scaling, because if 2 to the 40 is enough, then 2 to the 50 is also enough, right? So this with a little bit of the like compensation on the scaling factor part, then we can still use the composite scaling, of course, but we might not be able to use a very compact size of the scaling factor. And so in the previous slides, we talked about the implementation of our composite scaling method and applied to several workloads. So our implementation is not public yet, but we are planning for open sourcing our composite scaling implementation in the OpenFHE, and please stay tuned. Yeah, this is the end of my talk, and yeah, thank you for listening, and yeah, thank you.